Hey, in this video I want to introduce interface classes. An interface is a completely abstract class. Interface classes are typically referred to simply as interfaces, but I refer to them as interface classes in this video just to avoid some confusion, because of course we have interface files, interface and implementation files, and so I simply want to differentiate between interface classes and interface files. Again, interface files are typically header files, right? But with interface classes we are referring to purely abstract classes. In the previous examples of abstract classes, some of those classes had implemented, or in other words defined, functions, but an interface class is a completely abstract class, meaning it does not have any defined or implemented member functions. All of them are pure virtual functions. C++ actually does not have the concept of an interface as a built-in feature, but we can implement an interface as an abstract class when, as part of the definition of that class, we only provide pure virtual functions. An interface class specifies what a class must do, but not how. Instances of derived types, in other words the concrete classes, can share common functions that are defined or implemented differently based on the type. For example, a shape class may have a draw function that specifies that a shape can be drawn, but not how. Shape is an abstract thing, right? But a line and a circle is also a shape. And let's say we have a line and a circle class. Then in those classes we can implement the draw functions as needed to draw those specific shapes. Classes that inherit from an interface class must implement the interface, meaning that those classes must implement the pure virtual functions of the interface class. You can think of this in terms of a contract. The interface class guarantees that one or more member functions exist, and that those are implemented in the classes that derive from it. The prototypes of the pure virtual functions in the interface class and the implemented functions in the derived class must match. A quick example of some of the conventions that you might see with interface classes. Names of interface classes are typically prefixed by the I character, such as class iShape. And then within the body you'll have the pure virtual function such as draw, for example. Another convention that you may see is I underscore followed by the class name, but of course then you have to type that additional underscore. In this example, let's say we have this game level class, and this is responsible for spawning things into our level, so we can call some spawn function on that and it can spawn something. Now, of course, spawning something into a level is typically a map in a game, right? And spawning refers to something entering our game level or map. Let's say you have some level in a first-person shooter game, then you can define a spawn point for the player to spawn, but of course we can spawn other things as well. So we can spawn maybe chairs flying across the map, or asteroids that the player has to avoid, or aliens, right? They can be maybe friendly or they can be an enemy. The game level is not completed here, this is just an example, but we can already see some of the issues that we'll have with this. Because each time we create a new class and we spawn something, then we have to create a function in here. Maybe we want to spawn something else now, such as a creep, right? Like in one of those MOBA games or a book or something else, then we have to go and implement a function for that in the game level. So then we have to go and implement spawn book or whatever, right? So this is not an elegant solution. Instead, what we want is a specific function that says spawn, and maybe it can take in a pointer to a type of an abstract or an interface class, and then we simply call spawn on that object. Alright, so look at how we can do that next. Okay, let's look at this example. I have this interface class, which I called iSpawnable. In the public section, I have a pure virtual function, which I called spawn. And then I have, for example, I have a player character and an alien classes, and then I can publicly derive from iSpawnable. In the public section, you can see I do virtual void spawn override. All I'm going to do here is I'm going to print out player spawned, or in the case of the alien, I'm going to print out alien spawned. Now I also have this class called game level, and in the public section this has its own spawn function, so this does not derive from iSpawnable, alright? This has its own spawn function, and as a formal parameter there's a pointer to a iSpawnable. Remember that the function is virtual, pure virtual function in iSpawnable, so if you pass an object that derives from iSpawnable into here, then it's going to call the appropriate function on that object. Also, just to reiterate, we cannot instantiate an abstract class, and that also goes for an interface class. Scrolling down to main, I construct level 1, which is of type game level. We want to spawn things in our game level, so we create those things first. We create a player of type player character and an alien of type alien, and then I simply pass in the addresses of those in. And remember that the formal parameter of the spawn function in the game level is a pointer to type of iSpawnable. Of course, you can also make this a reference to an iSpawnable constant. For this example I used pointers, but in the next example, just to mix it up, I'll do references to constants. Okay, so that's what I'm doing here. Level 1, I want to spawn a player, and then next I want to spawn an alien. Pull and run that, and we get player spawned, alien spawned. I'll just copy that, and we can go and create another class, and now implement that spawn function for the chair as well, and I'll do level 1.spawn, and I'll spawn a chair as well. Pull and run that, and now it spawns a player, an alien, and a chair. This was just a silly example. Again, I'll scroll up here. The high level concept or idea is I want something to be spawnable. I basically want something to have the ability or the property of being spawnable. Okay, if you want to model something in that way. So I create a spawnable interface and the relevant pure virtual functions. Now I would like to note that this prototype should match what you have in the derived class. For example, in the alien class or in the chair class, let's say I change the prototype. You can already see that we'll get a squiggly here. Member function declared with override does not override base class member. I'll just undo that. That is it for this silly example. We'll move on to an exercise now. As an exercise, go and define a printable interface class. Let's say we want to do cout and some instance of a class. Now of course the type of that instance then derives from the printable interface class. As a hint, the printable class must overload the stream insertion operator. Another hint is that the printable class must have a pure virtual toString or print function, and I'll have to think a bit about the formal parameters. Go ahead, pause the video and attempt this exercise. Starting off, this is not the solution, it's just a justification for what we want to do. In this example, I have the player character class and an alien class, and let's say for each one of those I want to overload the stream insertion operator, so that let's go back to main here. So that I can do this, I can instantiate player or alien, and then I can do cout player and cout alien, right? Now you can see the problem with this. Let's say I do another class and I also want to print out the state of that using the stream insertion operator. So a kitten class or a chair or whatever it is that we want in our game, for example. Now each time we have to go and overload the stream insertion operator, and we have to provide the appropriate formal parameters for the right-hand operand, for example. You can see the player parameter is of type reference to player character constant, and then we also overload the stream insertion operator for the alien class, so the right hand operand is going to be a reference, or in other words the second formal parameter is going to be a reference to an alien constant. That is so that that can take in an argument of type alien. Again, if I do another class, let's say call it kitten or something like that, then I have to make sure to change the formal parameters again. The point with an interface is reusability, so that we can derive from that interface. So alien can derive from printable, player character can derive from printable, and in this way our goal is to make a more abstract version of this overloaded stream insertion operator, which has for the second parameter, in other words for the right hand operand, it will then take in a reference to that interface type instead of the particular class. Again, the goal is to create reusable code, because in this case we are having to duplicate stuff, and then instead we can provide specific implementations in the classes that actually derive from the interface. So let's say the interface class has some toString function or some print function that it will invoke when we do cout player cout alien. Instead of doing this here, we are going to do alien.toString, for example, player p.toString, and of course we can do that. Instead of doing it in this way, we can do that using virtual and interface class and virtual functions. Now in this case, the overloaded stream insertion operators are not defined as friends of those classes, because they do not need to have access to the private members. But of course, if you need access to print out the state of a particular object, you need to specify them as being friends. But the thing is, if the stream insertion operator is more generalized, where the right-hand operand is of type, let's say, printable interface, of course you can then pass in a child, so something that derives from the printable interface. And then again, what you're going to do in that generalized stream insertion operator is you're going to do a function call, but of course you implement that function call, or in other words implement or override that function in all of the classes that are going to derive from the printable interface. And because you implement that particular function then in the child class, that definition or implementation will of course have access to the class's private members. So in that way, as you'll see in the next example, we actually do not have to specify the stream insertion operator as a friend either. Okay, this is not the complete solution, but just to start off with here, I have the iPrintable class. and I specify the overloaded stream insertion operator here as a friend. The right-hand operand for this operator is going to be a type of iPrintable or something that derives from it. So for the second formal parameter, I have a reference to an iPrintable constant, which are called RHO for right-hand operand. And of course, on the left again, we have the reference to the output stream, which I simply call output. Then in the public section, I have a virtual void toString function, and this is a pure virtual function. And then I also have the destructor. Here we have the definition for the overloaded stream insertion operator. Now, if you think for a second, what do we want to do in here? Let's go back to main, for example, and you can see we'll actually get an error here. I construct player of type player character, alien of type alien, and we'll get an error. Those are currently considered to be abstract. Okay, so we want to do something like this. We want to do console output, the stream insertion operator, and player, right? Or alien. What do we want to have happen when we call this? Well, in the definition of the stream insertion operator, we can do right-hand operand dot toString. Okay, we do console output and an instance of player character. This will take it in as the right-hand operand, and then it will do right-hand operand dot toString. Okay, so let's go down and implement that in player character now. ToString is going to be const here. And of course, we want to do something like this. But if you think about this for a second, it doesn't really make sense, because in the overloaded stream insertion operator, we pass in the stream. In our example is console output, so cout, we're going to pass into here, right? What we can do is we can pass output into that toString. So we want to pass that around, so we pass that into the toString function, and we need to make sure that the toString function can actually accept the cout type. And how do we do that? Well, we've done it right here. So all I can do is copy and paste that, and then everywhere here where we implement it, we have to make sure that we pass that in as well, and then we can actually use it. So what does that mean? This statement right here is going to put the string literal, this character string out to the output. Where does that come from? Well, we pass it in from the overloaded stream insertion operator over here. We are going to pass cout in. Okay, we have a reference to that, and we pass that reference into this function, which also accepts, as defined, an argument of type output stream, which again in this case is also going to be a reference to type output stream. Now I want to do something similar in the alien class as well. Okay, let's go back to main, and let's look at this statement. For example, we do cout alien. What's going to happen? That's going to call the overloaded stream insertion operator, which is defined right here. Okay, we are going to pass in console output as the first argument, and alien, which is an iPrintable because it derives from that, as a right-hand operand. Then we do right-hand operand, in other words alien dot toString, and we're going to pass in that reference to the console output to the toString. Again, it can take that in because as a formal parameter, it has a reference to a output stream. So let's look at the definition now of the overridden toString function in the alien class. When that gets invoked, we are going to print alien join the game to output. The output again is what? Cout, because we are going to pass that in. We are basically threading that through, right? So output here is going to refer to what we have on the left, which is cout. Let's pull and run this and see if we have any errors. That seems to work fine. Human player joins the game, alien joins the game. But we can now also do something completely unrelated. Let's say we have a chair class which now publicly derives from printable as well. We implement the toString function for that, and we do the output that chair has spawned in the game. Now in the main function, we can do console output chair, pull and run that. And now we get a human player joined the game, alien joined the game, and a chair spawned in the game as well. So as you can see, we can now use that interface for seemingly unrelated classes. All we have to do is we have to implement the toString function, or in other words, we have to implement the interface. Now another thing I'd like you to notice with this example, if you think about it for a second, you may have picked it up already actually, but I'll just scroll up here to the interface, the iPrintable interface. We typically do not specify protected or private members in an interface. We only have the public section that we need, and of course because those are public, we do not need access to the private members, so we do not need to make the stream insertion operator a friend of this iPrintable interface class. Comment that out. I use this here as a demonstration, but remember this is a different formal parameter than this one right here. Okay, these are not the same. This formal parameter belongs to toString. This formal parameter belongs to this operator right here. And what do I mean by this? Well, this is now the declaration and definition of the stream insertion operator, and we are accessing a public member. Okay, the member is not going to be private or protected. So in other words, the stream insertion operator actually does not have to be a friend. Also remember to return the output in the definition so that you can chain the stream insertion operator. Okay, otherwise you cannot do this right here. Build and run this and you'll see it still works fine. So as demonstrated, for the most part you will not need friends for your interface classes, because your interface classes will typically only have a really minimalistic public interface, or in other words, pure virtual functions within the public section. Before we wrap up, let's talk about interfaces as properties. If you think in terms of inheritance, then the child class is the parent class, right? At least if the child publicly derives from the parent. You can also think of interfaces in terms of properties. Some of the examples that we've seen in this lesson is, let's say we want some class to be spawnable, so we can spawn objects or game elements into our game world. For example, as we play a game, we may want to save our progress, or in other words, write our progress to disk, so that when we load the game back up again, we start the program up again, then we can load the state of our game or our progress in the game, because of course that is not going to stay in your RAM. Child classes implement the interfaces to have or to use those properties. As a silly example, we have an alien class which publicly derives from iPrintable, so a printable interface, and also publicly from iClonable, so a clonable interface. And of course within the definition of the alien class you want to implement those interfaces. But you can think, okay, this alien class has the property of being printable, and it has the property of being clonable. So maybe as we play the game and we don't destroy the alien, after some time it will clone itself. Just as a silly example, also let's say you have a player character. Of course you may want that to be savable, so you can save the state of your player to disk. Now I'm talking about this, but we haven't really talked about those streams and saving to files yet. That will be done in an upcoming lesson. But just as an example, right, you want to load or you want to save your state from disk. And you can think of that as being a property that some class can have. Instead of thinking in terms of inheritance, a barbarian or a wizard is a player character. Or in another example, maybe I have a circle or a line. Those are shapes. A line is a shape and a circle is a shape. Instead, we can think in terms of properties. We can print some shape, so we can print the line or the circle and so forth, right, you get the idea. To wrap up this lecture on interfaces, remember an interface is a completely abstract class, so we provide only public pure virtual functions. Interfaces typically will also not have any member variables. As I mentioned, interfaces are typically prefixed by the I character, and for the most part you'll be using interfaces instead of abstract classes where possible, but of course in C++ we are not really constrained in this way. Another important point is that you have to consider backwards compatibility when designing the interface. As I've demonstrated, a change to the signature of the pure virtual function in the interface class will require updates to the signatures of the implemented member functions in child classes, and of course you want to avoid that because you can have many child classes. Finally, be a champ and always remember the virtual destructor. Whether you have an abstract class, an interface, or just some virtual function in your parent class, you want to make sure to provide a virtual destructor for the cleanup process. Alright, that is going to wrap up this introduction to interfaces. I hope you find it useful, and I'll see you next time.